So we actually had quite a bit of mathematics so far, and the advantage of that mathematics is because now we can apply all of that about public key and RSA, and we can understand everything. In DES and AES, the problem was you asked several times, why is this table like that, and we have no answer, right? But here the beauty is that everything is mathematically set. So we have the answer for everything, why it is done this way. All right. It does require a lot of this Galois field stuff, but that's why we taught you all this Galois field, Chinese theorem, and Fermat's theorem, and Euler's quotient, because all of that is used. So first thing we'll talk about is public key encryption, and then we'll go into RSA, and then how to optimize that and all the other issues. So public key was invented by Diffie and Hellman. We heard that name before someplace, remember? And these guys were at Stanford, and in 1975 they said that we could do this. They didn't have an exactly working method, but they had an idea. The idea was that we could use two keys. Key 1 can be used to encrypt, and key 2 can be used to decrypt. All right? And the keys are interchangeable. If you use key 2 to encrypt, key 1 can be used to decrypt. So it doesn't matter which key, but you have a key pair rather than one key, such that you can use one to encrypt and the other to decrypt. All right? And therefore, one key you can make public. Anybody can encrypt and send it to you, but they cannot decrypt it, because the other key you keep it private. All right. So the sender only knows the public key, and therefore asymmetric. So previous one, both parties, the sender and the receiver, knew a secret key, and both of them had that same key. Right. So that was called symmetric. This one is asymmetric because the sender doesn't know what key you are using. All right. So this is asymmetric. So here's an example. I'm just going to start with the example, and this is actually based upon the RSA. RSA are at MIT, and so in RSA, whatever the message you want to encrypt, it has to be made a number first. Okay, you make that as a number, and then your key has two numbers. Your key has 3,187 or 107,187. So here in this example we have two keys. The first key is 3,187. The second key is 107,187. So the way these numbers are used is that you raise the message to the power 3, and you take mod with the second number. So suppose your message is number 5. Okay. So you will raise it to power 3. 5 raised to 3 is 125. Mod 187 is 125. So you will just send 125. The other side can decrypt it by raising it to power 107 and mod 187. Now you have done this homework. 125 raised to 107. Was this a homework problem? I thought I gave this as a homework problem. Figure out what is this value whenever we talked about mod. But anyway, if you remember, this answer was 5. So if you do this, you will get 5. And just as a reminder as to how you did this was that you expanded 107 into powers of 2. So you expanded 107 as 64 plus 32 plus 8 plus 2 plus 1. So you can calculate 125, then you can calculate 125 squared, then 4 and 8 and then 16 and then 32 and 64, and then use the powers that you need to multiply together to get 5 at the end. So every time the numbers would become less than 187. So you won't just raise this whole thing, you will decrease it to less than 187 every time, and then with small numbers you will finally end up with 5. Now, so anyway, so you see an example here where there are two keys, If you encrypt with one, you can decrypt with the other one, and I could have done the other way around, where I could have taken the message and encrypted with 107, and then the other person would have decrypted it with 3. Alright, so what is the difference between symmetric key and the public key? Symmetric key is what we were doing so far, public key is what we are going to do now. First of all, same algorithm is used with the same key for encryption and decryption. Actually, when we say same algorithm, I mean, one has to understand that in AES, the decryption algorithm is slightly different than encryption algorithm. You have to rearrange the keys, and you have to have inverse functions. But the algorithms are very similar still. Similar algorithms are used with the same key. In public key, it is the same algorithm actually, but the keys are different. Well, the algorithm doesn't have to be the same. Actually, they have to be similar, but in RSA at least they are same. Sender and the receiver both share the algorithm and the key. Here, the sender and receiver have one thing that they don't share. Right? So the keys must be kept secret. So the two guys know the key, but the third, any other person doesn't know it, right? Here, one of the two keys must be kept secret. So private key cannot be divulged. It must be impossible or at least impractical to decipher a message if the key is not available. Right? Here, it must be impossible if the secret key is not available. So that part is still same, if the private key is not available. Knowledge of the algorithm plus samples of the ciphertext are insufficient to determine the key. Here, knowledge of the algorithms plus one of the keys plus sample ciphertext are insufficient to determine the other key. Alright, so the only thing secret is the private key. That you should not be able to determine. So everybody understand now the main difference is that previously we had nothing public. Now one thing is public. You can put it on your website that this is my public key. In fact, that is what is called your certificate. When you get a certificate, all you are getting is a public key, and you are sending the certificate to anybody who asks for it. Say, okay, here's my certificate. All they are getting is your private. They are getting is your what key? Public key, and you keep your private key with you. So, if you want to get authentication and secrecy, that is what previously was not possible, is that you want to make sure that if A sent you some message, you can go to the court and say that A sent me this message. So for that, what A has to do is, he has to encrypt the message with its private key, and then encrypt it again with your public key. B is you. So A sends the message with A's private key, its own private key, and then encrypts it with B's private key, and sends it to B. What B can do with this message? How can it open it? How can it open the outer lock first? It uses its private key, so it opens that box. Then what does it do here? A's public key, and anybody in the code can use A's public key to open and find out what the message is at this point, right? And it proves that A sent it because nobody else has that. Nobody else could have produced that message, because nobody else has the private key. So you can immediately see that it gives you a lot more power than before. Right? So now you can use it not only for encryption and decryption, but you can also use for digital signature. And you can use it for key exchange. Why key exchange? Because this is lot of calculation. M raised to raising a power and taking a mod is lot of work. So you really don't use it for encrypting any messages. You just use it to encrypt the keys and send it to the other side, and then you use the secret key. Secret key is very easy to compute. Keys are small, 56 bits. Here the keys are this big, 160, 200 digits, 640 bits. So computation is very slow. So, and second thing is the M has to be less than P. I mean, one thing you should notice that in every mod thing, you cannot send a message which is more than 187, right, in this example. So, the message has to be smaller than the key size. So, if your key size is 1024, your message has to be less than 1024 bits. Right? So, it's good for sending the keys rather than sending the messages. All right. So, now there are many algorithms for public key. RSA, elliptic curve, Diffie-Hellman, DSS and all that. We will talk about them later on. So, some of them are good for one and some of them are good for the other and so on and so forth. RSA is good for all three. Elliptic curve is good for all three. Diffie-Hellman was good for key exchange only, and then DSS is good only for signature. DSS, by the way, stands for Digital Signature Standard. So, it's good only for signature anyway. So, but you can do all three. So, what is it? How do you do public key? So, this is what Diffie-Hellman said. Diffie-Hellman said we need to find a function f such that calculating f of x is easy. It's a one-way function, so I can calculate, but I cannot invert it. So, it's like any other hash function, right? You can do one way, but you cannot do the other way. But at the same time, it has to have this other property that if I know the key and x, I can do this and I can do the inverse very easily. So, if I know the key, then I can invert it easily. But if I don't know the key, then I can't invert. And so, people were thinking about how to find these functions, and it took some time before RSA came up with the first method to do this. All right, before I go into RSA, which is actually the next slide, these are some of the common properties of most of the public key systems. First of all, you cannot do exhaustive search because the keys are so long. So, that is out. It says greater than 512 bits. I should have said here 1024 bits today. Maybe that is dated. And it basically relies on mathematical difficulty, that you can't do some calculations easily. And so we know what the method problem is, but we can't do this, right? And we use very large numbers, and therefore it is very slow. All the public key schemes are very slow. So RSA again in detail. RSA are Rivest, Shamir and Edelman at MIT, 78, so not very far, 4 years later. Then Diffie-Hellman, and they found out that exponentiation is easy but log is difficult and factorization is difficult. We just said that in the previous chapter, right? So based upon that observation, they said let's just design an algorithm which uses exponentiation, and because the exponentiation takes log n cube operations, factorization takes log n times log n. Okay, so that is almost close to n. That's very difficult. So basically, we already saw this. I'm going to just repeat everything I have said in the example. So you have two keys, E comma n and D comma n. If you want to remember, E for encryption, D for decryption, right? But E comma n and D comma n, and then for encryption, all you do is you raise m to power E and do mod n. For decryption, you raise the ciphertext to power D and do mod n. Very simple. No tables, I mean so far. No tables, nothing to be done, just basically you have to raise the power and do mod. The question is, how do you find E and D? So they specified the algorithm also. You select two large primes P and Q, where P is not equal to Q. they have to be prime numbers though. P and Q have to be large prime numbers. Okay. Then you calculate n equal to P times Q. Now you calculate this torsion function of n, which will be equal to P minus 1 times Q minus 1, right? Everybody remembers that? The torsion function for a product of primes is equal to, right, because torsion function for P is P minus 1, torsion function for Q is Q minus 1, and therefore torsion function for n is the product of the two. Right, so calculate that. Then select E, any number which is relatively prime to phi. And then select D, which is the inverse, and that's why we needed that tabular method to find the inverse. Select D, which is the inverse of E mod phi, and then those are the two keys, D and E's. Then you tell the world E comma n, and then you keep D comma n private. Now here's the thing, everybody knows n. If somehow they could factor out n, then they know P and Q, and then they can figure out everything. They can figure out, given D, given E, they can figure out D. But the main difficulty is that you cannot factor n. Now, here are several steps here. I just want to make sure that everybody understands every step. If it is not clear, please read it again and ask as to what that step is. Select two primes P comma Q, then multiply them, find their torsion functions, and then select E, which is relatively prime to phi, and find D, which is inverse of E. That's all. Here's an example again. Our example we already gave, so I'm not going to give the example again. We had that example 3 comma 187. So now to select D or E, remember DE is equal to 1 mod phi, and so E is selected first. So E you can select arbitrarily. So for example, 3 is a good number, 2 raised to 1 is not a good number, but it is potential number. Generally it is because you have to raise power and multiply and all that. It is good to have some power of 2 plus 1. So 2 raised to 1 plus 1 is 3, 2 raised to 4 plus 1 is 17, 2 raised to 16 plus 1 is whatever number, 64,000 some number plus 1. So that makes exponentiation easy. And then find the inverse of E using Euclid's algorithm, and generally the public key should be the smaller one, because that way everybody has to do that, and the private key can be large. While the public key can be 3, the private key should not be 3. Because the private key is 3, then anybody can use Chinese remainder theorem with 3 messages and different moduli and then try to find out. So that would be very weak. You want to have private key large numbers. I mean this part to be large number. Public key can be small. Just this part can be small, not the other n is big anyway. That is common to both. And both are, again this one says 512, but as we see towards the end of this chapter, that really 1024 is what is today a good number. So let's try one more example. We want to get a key, so we get two prime numbers 17 and 11. Obviously these are not the numbers that you will really use in any real world thing, but just to, for our example, we will just take two prime numbers 17 and 11. Any two prime numbers will do. We multiply them, we get n equal to 187. That's what we had before, 187. Phi in this case is p minus 1 times q minus 1, which is 16 times 10, which is 160. So we have to find something which is relatively prime to 160. So it cannot be 2 or 5. Anything else will do. Right? So we select 7. Then you find the inverse of 7 mod 160, and you can do it by inspection or you can do it by the table. Anyway, you will get 23 as the inverse. Best thing is to do by table, because if you are going to do by inspection, it will take quite a bit of time to find 23. With table, you are guaranteed, with a small number. So your keys are 7 187 and 23 187. I could have selected, instead of 7, what number could I have selected? Any number? Anybody has another idea? I cannot select 5. I could have selected 3, then I would have gotten the same thing like before, 3 and 107. But if I could have selected, let's say, 13, and I would have gotten the second key. So there are plenty of keys for the same 187 mod thing. Now, how do you do exponentiation? When you want to do exponentiation, the best thing is to just keep squaring the number. And when you keep squaring, you get whatever number raised to 2, number raised to 4, number raised to 8, number raised to 16, number raised to 32, and then you add up the numbers there where the bits are 1. Right? So for example, if you want to calculate 3 raised to 129, you expand 129 and you get only 128 and 1. Right? I mean 2 raised to 8th bit is 1 and then last bit is 1. So you just calculate all the way up to, you square 8 times to get 3 raised to 128, and then you multiply by, and you have to do mod at every step. So when you do that, you will get 5 times 3, which is equal to 4. Right? Here is the program written in the book. I wrote it in Excel actually. You can write this in Excel. And this program that I have written is actually good for any number. So it doesn't have to be these numbers. Basically, I have programmed so that I put A here, B here, and N there. 3 numbers, and the table changes. And automatically gives me what is the value of A raised to B mod N. And this is basically to figure out, as written here, it was what is 127, 5 raised to 107 mod 187. The answer is 5. I mean, obviously, it won't help you in the exam because you are not allowed to use Excel. But it can help you in homeworks, and things like that, where you are allowed to use Excel. But you might as well write down this formula, which is equally good, this program. So what I have done here is, this is the binary expansion of the power. 107 here is 1 1, actually it's reading from this side, 1 1 0 1 1 0 1 1. That is the binary expansion. And then this C is actually the number up to that point. If we only had one bit, it would be 1. If we were 2 bits, that would be 1 1 would be 3. And then we had up to this bit, it would be 11. And if we had this, 107, and so on and so forth. And this is A raised to C mod N. So A raised to C mod N, if C is 107, that is 5. And all of these numbers are, basically less than 187 square. Because at every formula there is a mod 187 everywhere. All right, so everybody kind of knows how to do exponentiation. Although in the exam we will not ask you to do any of these large numbers or any of these things which will really require you to use big anything, but for small values of A, B and N we will certainly ask, so that you know how to calculate the keys and things like that.